In our previous lessons, we've been working a lot with linear equations individually. Now we want to look at a system of linear equations. A system contains two or more equations. We're looking for where the equations intersect or have the same value. This is primarily used by people looking to make comparisons between different options or compare multiple variables to see how they interact. We always want to check algebraically to verify that we have found the correct solution for the system. So for example, here we're going to start working on solving our linear systems by graphing. And we know how to graph equations of lines. We're going to graph two and see how they interact with each other. So the first line we want to graph would be y equals 1/3 x plus 8. So I'm just going to mark this in green. Now remember, when we have the equations, this is a slope-intercept form, so we know our starting point, the y-intercept, and the slope, how we would move from point to point on our line. So looking at our equation, we know that our y-intercept would be located at 0, 8, and so we'd mark that on our graph. Then we look at our slope, and our slope is 1/3, and that means we're going to be moving up 1 unit and to the right 3 units to find points on our graph. So we go up 1 to the right 3 and put our point, and continue and put our point. Notice how you've run out of space, so go back to your y-intercept and reverse your slope. Go down 1 and to the left 3 until you have a good set of points to create your line. We know lines are continuous. We're going to use those in between values, so we're going to connect them. So that's our equation graph for y equals 1/3 x plus 8. Now we're going to work on graphing our second equation, y equals -2x plus 1. And so again, we're going to mark this in blue. Looking at our slope-intercept form, we can see our y-intercept would be at 0, 1, and we plot that point. And our slope is -2. So that means we're going to be going down 2 units and to the right 1 to plot our points. We go down to right 1, down to right 1, and so on to get a good set of points. If we want some points to the left of our y-intercept, we reverse the slope, going up 2 and to the left 1. As always, they're continuous, so connect your individual data points. So we have the two linear equations graphed. What do you notice? We notice that the two equations intersect at a particular point. And where they're equivalent is the important part. That represents the solution to your system. So our solution is this point right here. That would be our coordinates -3, 7. Now, how can you check algebraically that you have the correct solution to your system? Well, the solution represents a coordinate on your graph, and a coordinate is made up of your x and y values. And our equations have both x and y's within them. So we're going to take the coordinates of this point and substitute it in for both x and y for each equation to make sure that it ends up with a true statement. If it's true, we know that we've graphed our system correctly and we have the correct solution. If it ends up being false for either of the equations, we'd have to go back and double check and make sure where our error occurred with graphing the lines to ensure that we get the correct solution. So let's check this. If we substitute -3 in for x and 7 in for y, and we follow our order of operations, our first equation here on the left, we'd end up with a -1 plus 8, which we know is 7. The one on the right, we'd have 6 plus 1, which is 7. They're both true, so we verify that we have the correct solution to our system of equations. So let's try another. Here we have the system x plus 4y equals -8 and y equals -4. And again, we want to solve this by graphing. Looking at our first equation, this is in standard form. And if we're going to graph it, we really want this into slope-intercept form. So we're going to take that equation in standard form and manipulate it into slope-intercept form. So in order to do that, we have to get y alone. That means we'll be subtracting x from each side of the equation and then divide every single term by 4. That would leave us with -2 minus 1/4 x. Now, we know how to graph an equation in slope-intercept form. First, we plot our y-intercept, and we know our y-intercept would be at 0, -2. So we're going to plot that point on our graph. Then we're going to move and plot points according to our slope, and our slope is -1/4. So we're going to go down 1 unit and to the right 4 to create our next point on the graph and continue until we run out of space. We go down 1, right 4, down 1, right 4. To get more points, go back to the y-intercept and reverse your slope. Go up 1 and to the left 4. So you'll generate a good set of data points. And as always, it's continuous, so connect them. Now we want to work on graphing our second line, and our second line is y equals -4. And we can see that the y-intercept would be at 0, -4. So we're going to plot that point. Now, from this point, we have to move our slope. And as we look at our equation, we have no value for x with a coefficient, so that tells us our slope is 0. That means every place that we go, we'll have to have a y value for a coordinate of being -4. So that could happen here, and here, here, and here. You have an infinite number of possibilities, and notice they're forming a horizontal line. Because your slope is 0, there is no change in your rate. So we have our second equation graphed. Now when solving by graphing, we want to see where are the two equations equivalent to each other. So are they intersecting? And yes, they are. We can see they're intersecting at this point right here. So it appears our solution would be at 8, -4. Now, to verify it algebraically, we're going to take 8 and substitute it into x for each equation, and -4 and substitute it into y for each equation. To verify algebraically, we have the correct location for our solution. So they really are equal to each other at the same place, same time. So again, substituting in, that second equation was just y equals -4, so -4 equals -4, we're good to go with that. Our first equation, substituting x and y, so we've got a little calculation to do here. 8, and this would be a -16, so 8 and -16 does in fact give us a -8, so it's working for both equations. We have the correct solution, and we know that we've graphed them correctly. All right, let's have you try one now. Can you solve this system of equations by graphing, and also check your solution? So we have two equations in standard form, and we're going to have to put them both into slope-intercept form so we can graph. So let's start with the first equation, 3x plus 2y equals 10, and we're going to undo that to get y alone, which means we're going to subtract 3x from each side of the equation, and then divide every single term by 2, which leaves us with y equals 5 minus 3/2 x. Now to graph this, we're going to look at our y-intercept, and we know our y-intercept would be located at 0, 5, and we're going to plot that on our graph. Then we're going to move according to our slope, and our slope is -3/2. So we're going to go down 3 and to the right 2 to generate all of our points. If we run out of space going in that direction, we can go back to the y-intercept and reverse our slope, going up 3 and to the left 2. Once you have your series of points, always connect them with a line because we know that they're continuous and we can always use the in-between values. Now we're going to work on our second equation, 3x plus 2y equals 2. And we're going to have to undo that to get y alone. So our first step would be subtracting 3x and then dividing every single term by 2, which leaves us with y equals 1 minus 3/2 x. Again, we're going to start with our y-intercept. Our y-intercept is at 0, 1, so we plot that point to start. And then our slope is -3/2, so that means we're going down 3 and to the right 2 again. So we're going to plot our series of points and connect them. So remember, at this place, once we have both of the equations graphed, we're looking to see where they're equivalent. Where are they equal at the same place, same time? And that's typically when they intersect. Well, if you look at these lines here, they're not intersecting. Will they ever intersect? No, they will never intersect because they have the same rate of change, which is -3/2. So again, from point to point, you're always going down 3 and to the right 2. So no matter where your starting value is, the y-intercept, as long as you have the same rate, they will never touch. So what does that mean for us when we're talking about a solution? If they're never going to be equivalent at the same place, at the same time, that means we have no solution. Now, lines that have the same rate of change, perhaps you've heard this term before, they are parallel to each other. So since they have the same rate of change, we said they're never going to intersect. That's why we have no solution for this system of equations. Let's try one more. We want to solve this system of equations by graphing and, of course, verify your solution. So the first equation we see is in standard form, and we have to manipulate that to put it into slope-intercept form so we can graph it. So we have to get y alone. Our first step here would be subtracting 4x from each side of the equation and then dividing every single term by -2. So we have to be careful with our division. When I divide this by -2, it would be a positive, this will be a negative, and this would be a positive. So we end up with the equation y equals -4 plus 2x. Now we're going to start graphing. Our y-intercept will be at 0, -4, so we plot that point. Our slope is 2, so from this point, we're going to go up 2 units into the right one until we run out of room. Then we can go back to the y-intercept and reverse our slope, going down 2 into the left one. And as always, we can use the in-between values. They're continuous, so we connect them. The second equation is already in slope-intercept form, so we can start working on graphing that. What we need to do is think about our y-intercept, which we know is at 0, -4, so we can plot that point first, and then go our slope. Our slope is 2, so we're going to go up 2 into the right one each time until we run out of space, and then we'll go back to the y-intercept and reverse our slope, going down 2 into the left one. And again, once we generate all of our points, we can connect them because we know we could use the in-between data values. It's continuous. So here is the graph of the two lines. Well, what do you notice? They had the same y-intercept. They had the same slope. Essentially, they are the same line. So, how many places are they equivalent to each other? Every single place that they're touching is a solution. They are equivalent. So how many points are on a line? Well, we have an infinite amount. Therefore, we have infinitely many solutions. And again, why is that happening? It was the same line. They had the same y-intercept. They had the same slope. So every single point generated for the equations would be equivalent. Therefore, we have infinitely many solutions. So some of the big takeaways. When we're solving systems of linear equations, we typically have 3 types of solutions appear. We can have one solution where the lines are intersecting at a point. We could have no solution where the lines will not intersect because they have the same rate of change. They are parallel to each other. Or we have infinitely many solutions because the lines have the same y-intercept and the same slope. We also learned how to verify the solutions for our system when they do intersect at a particular point. So let's try one more. If we have this system of equations, could you prove whether or not the point 2, 3 is a solution? We have 2 methods to do this. We know the point 2, 3 is a coordinate that has an x value and a y value. And our 2 equations both have x values and y values. So when we were doing the algebraic check, we were substituting the values for x and y into the equations and trying to make sure that they were true. If they are, it verifies we've got the correct solution. So I'm going to take my value for x and put it into each equation, and the same for y. And then simplify according to your order of operations. Well, we know 2 minus 1 is not equal to 3. And we know -2 plus 3 is not equal to 3. So because it's false for both equations, it would not be a solution to your system. Even if it was true for one of the equations but false for another, it still would not be a solution to your system. Solutions have to be true for both equations. Now, if you didn't realize that you could do the substitution like we'd done before, you could always graph your equations. The first one has a y-intercept at -1 and a slope of 1, and the second one has a y-intercept of 3 and a slope of -1. And we could see if they are intersecting at the point, 2, 3. So if we look at your graph, our first line is in green and our second is in blue. And notice that they do intersect, but they're not intersecting at the point 2, 3. Therefore, it's not a system of equations. So you could also prove it graphically. Now, which method was quicker? If you're just asked to prove whether or not it's a solution, it is quicker just to use the substitution method, but you are always welcome to do the graphing if you so choose. Now it's your turn to do some more practice, and then we'll review in class.